So we come to the thorny issue of gravitational potential given the symbol V. Now this is an area of gravitational fields that a lot of students really struggle with. And to be perfectly honest, this is one of the areas which I find difficult to teach because it's quite a slippery idea in terms of the definition, in terms of the calculation, in terms of what it means. So it's definitely something which requires a bit of thought. Now do check with your specification. I think most exam boards do expect you to understand this to some level, but there might be slight variations. So we're going to talk about, first of all, the definition. And then we'll try to piece all of this together, and we will look at some calculations on the next slide. So first of all, the definition, it's the amount of work done by the field, that's important, per unit mass on the mass as it moves from that point to infinity. Okay, right, so what have we got here? We've got our object, let's say in a low orbit position, so it has some gravitational potential energy. And if we then compare that to a situation where it is very, very far away, and we call that infinity, but we just mean deep space. So we mean the effects of the gravitational field are negligible. So at this position, the gravitational potential is zero and the GPE is zero. Now this is quite an odd idea because we think, well, how can it be zero? Because if you imagine we are totally outside of the effect of the Earth's, in this case, the Earth's gravitational field, then we cannot have any gravitational potential energy or gravitational potential. So generally we're talking about the change in gravitational potential energy. So the gravitational potential actually increases from a negative value when we're somewhere in the field to zero when we are at an infinite distance. Right, so that's our definition. And let's look at the next stage. We've got V, which is not a very helpful symbol because normally we associate V with electric potential or potential difference. And there are similarities, as we will see. But normally we'd write this as capital V and then with G or grav. So gravitational potential is minus Gm over R. Okay, so it looks very similar to our expression for little g, but that was divided by R squared. Now we could derive where this comes from, and we'll look at that later on. But the key thing to realize here is it's not an inverse square relationship, it's inverse proportional. So gravitational potential is inversely proportional to distance. Right, so let's imagine how we would draw this on a graph. So we've got V on the y-axis, we've got distance on the x-axis. Okay, so this negative sign is quite important here. And in fact, in the calculations, we will include this value because we have a negative potential when we are close, let's say when we're at the Earth's surface, RE, and that will get less and less negative and it will approach zero, and this will be asymptotic as well. So that negative sign is important, and the relationship here is inverse proportional rather than inverse squared. Right, so let's go back to the definition. So it's the amount of work done by the field. Well, the field isn't doing any work here. It's not attracting. If we were going the other way, if we were going from infinity to near to the Earth's surface, then the field would be attracting the object and doing the work. But we have to put the work in. This requires energy input when we're moving to infinity. And this is why it's a negative value. So the energy is input. And it's a little bit odd. Now, there are other definitions. Sometimes you could define this as the amount of work done by the object or energy input. But certainly WJC, WJC, defines this by the field. Right, so again, let's look at this in some other ways. So if we compare this to gravitational potential energy, which is related but not the same, that is the energy an object has due to its position in a gravitational field. But this is the energy per unit mass. So we've actually, this gives us the units of joules per kilogram. We've also talked previously about electric potential, which is the energy per unit charge. So that is given the symbol V. That's E over Q, whereas we have E over M. So why is this useful? Okay, so if we wanted to work out the energy or the work done, or indeed the change in potential energy, all of which are the same things, If we can work out the change in gravitational potential, that's delta V or delta Vg, if we multiply that by the mass, that will give us the gravitational potential energy or the change in gravitational potential energy. Right, so this is very abstract, very difficult. I think the best way to put all of this into context is with a calculation, and we'll do that in a few minutes' time. Just before we move on from this screen, something to consider, and very often this comes up in the as an exam question, is if you're given or shown in the exam a graph of V against R, you may be asked to calculate the field strength. And what you'll need to do is to find the slope. So what you could do is draw a tangent at the point where we're told the radius, and then work out the gradient at that point. The gradient is the y divided by r, which is v over r. V we know is gm over r. If we divide by r again, that gives us gm over r squared, which we've already defined or derived in an earlier video as gravitational field strength. So that's, if you can understand the derivation of this, that's brilliant. Or you can just remember that the slope, the gradient at a point of a potential distance graph represents the gravitational field strength. Just before we move on to a practice worked example, I'm going to mention equipotential surfaces. Again, just check with your exam board whether you need to know about this. Certainly, Workbook do include this. This is actually, even though it looks or sounds quite complicated, this is actually relatively straightforward. So the definition, and you might be asked to write this in the exam, is an imaginary surface. So it's a surface because obviously we've drawn this as a two-dimensional drawing, but this represents a three-dimensional space. So it's the surface, it's not a physical surface, it's an imaginary surface of a sphere on which all points are at the same potential. Now that shouldn't surprise us, because if I work out the potential of my object here, let's say this is a satellite, or it could be the moon, that depends on the mass of the Earth and the distance between the center of masses. So if I move it over here, it'll have the same potential. In fact, anywhere on this circle, on this equipotential surface, it will have the same potential. But if I move further away, or indeed closer, then the potential will change. But anywhere on this circle, 2D, or surface of a sphere, 3D, the potential will be the same. And typically, you might get given a drawing where you're given values, and you have to work out the difference or identify that they're the same because they're on the same curve, the same equipotential surface. So the questions related to this tend to be quite straightforward. So let's look at a worked example. So find the gravitational potential. So the most important thing here is to use the right formula. We're so used to gravitational potential energy that a lot of students just get confused between that and what we're trying to find. So we're not trying to find, for part A, the gravitational potential energy. We want the gravitational potential. So it's this formula here, and we will include the negative because by definition, that is important. But once we have the right formula, then the calculation should be straightforward, as long as we take into account that the height is above the Earth's surface, so we need to add that onto the radius. So we've got the right formula, hopefully. Big G, we know that. The mass, there's only one mass, that's the mass of the Earth. And we're going to divide by R. Be careful, it's not R squared, it's just R. Very, very common mistake. And we need to add together the radius and the height in meters, so this is times by 1,000, and we're going to get this value here. So expect a large value, and the units are joules per kilogram, as we've mentioned already, the work done per unit mass, or the energy per unit mass. And you would expect to include the negative sign, because by definition, this is a negative value. That on its own, I think, doesn't really mean that much to us because we're not used to thinking about joules per kilogram. But part B hopefully puts this into context. So we're told the gravitational potential at the Earth's surface is this value here. So we would expect that to be larger than at the height of the satellite, because we're moving away from infinity, we're getting a larger negative value. So we're trying to find the change in potential energy as we move between these two positions. So all we need to do is to work out the difference between these two potentials. Now, we could take into account the negative values here. So it would be minus 5.5 minus minus 6.27, and they're both 10 to the 7. For simplicity, again, we could just disregard the negative value and just work out the difference between the two positive values, so the magnitude of the difference. So either way we do it, it is the difference. So 6.27 take away 5.5, 10 to the 7, then multiply by the mass. So this expression here, we're probably given that in the formula booklet, but if we're not, then we know by definition the potential is the work done per unit mass. So if we want the work done, or the energy, or in this case, the potential energy, it's going to be the change in potential multiplied by the mass, and it's the mass of the satellite, not the mass of the Earth. And we would expect to get a really large value, as in this case, because we're moving a very large mass between the Earth's surface and its orbital position. So this is in effect the amount of energy required to put this object in orbit. Now, in reality, it's a bit more complicated than that. But this is the difference in potential energy.